All right, in this chapter and section, we're going to be looking at concentrations of solutions. We'll be talking about how much stuff is in a given solution. So our definition of concentration is just the amount of solute dissolved in a standard quantity of either solvent or solution. The definition we're going to be going with in this chapter and in the first semester is going to be in a standard quantity of solution. And that definition is molarity. Molarity is defined as the number of moles per liter of solution. Here is in sort of an equation format, the molarity is the moles of solute divided by the volume of solution in liters. If we want to write this down as a calculation, we could put uppercase M for molarity is equal to the number of moles N over the volume of the solution in liters. And so there's the molarity, there is the number of moles, and there is the volume. All right. I want you to be able to solve for any of these. So, if you can get two of them, you can get the third. So, all right. So, a molarity calculation example says calculate the molarity of a solution made by dissolving 0.123 moles of sodium chloride in enough water to make 355 milliliters of solution. All right. So molarity is N over V. The quantity that we're looking for is molarity, so that's what we're looking for. That means that we need the number of moles and we need the volume. Well, the number of moles, of course, is 0.123, and the volume is 355 milliliters. Of course, we want to convert that into liters. So we'll just move that decimal point over three spaces to give us the volume in liters. And then three significant figures, we can do the calculation, and we'll get 0.346. Next, let's look at this problem. Molarity, we want to solve for moles. So calculate the number of moles of potassium nitrate in 451 milliliters of a 1.34 molar solution of potassium nitrate. All right, so the thing that we're looking for here is N. That's the number of moles. So we'll solve that equation for N. And when we solve it for N, we'll get molarity, and again, uppercase M times V. Our molarity is 1.34, and our volume is 451 milliliters. Again, we're going to write that as liters so that the units cancel out. Now, you'll notice here that this says 1.34 molar times 0.451 liters. And if you're trying to do dimensional analysis, you don't see the liters unit to cancel out here. That's because the molarity means moles per liter. So often when I'm writing this out, I will write it out so that I put moles per liter, and that way I can do dimensional analysis and cancel out the liters. And we multiply that out, and we get this number, 0.604 moles of potassium nitrate. So let's look at number 61 on our in-class assignment. All right, here we go. We've got everything set up. So now when we look at this, so first thing, whenever you're solving one of these, the first thing you want to do is to determine what it is that you're looking for. In this case, we are looking for the molarity of a solution, and there is our number of moles, and there is our volume. So molarity is equal to N over V. N, of course, here is 0.0345 moles. And our volume, it says exactly 400 milliliters. And what that does is when it says exactly, that means that we can use as many sig figs as we want. And we're going to convert that into liters. So we'll put that as 0.400 liters. Again, I'm just going to pick the same number of sig figs that I have up in the numerator for the denominator. All right. So make sure that's all clear. Okay. Let me adjust something. All right, I adjusted my light a little bit there to make it easier to see. So we'll put 0.0345 divided by 0.400. And you'll see the number that we get there, 0.08625. But since we only have 3 sig figs, we're going to go ahead and I'll go ahead and write this out, 0.08625. But we're going to round that to 3 sig figs, and we'll call it 0.0863 moles of NH4Cl. All right, so now on this next one, part B, you can see what it's looking for right away. It says how many moles. Well, the number of moles, that's N. So we'll solve our equation for N. N is equal to the molarity times the volume. Okay, our molarity, when we read this, our molarity is 2.20 molar. So 2.20. And again, since this is molar, I'm going to write that as moles per liter. So I'll put that as moles per liter. And then we'll multiply that by the number of liters. Here we've got 35.0 milliliters. I'm going to write that as 0.0350 liters, again, to keep the same number of significant figures. You'll see that the liters cancel out, and we're good to go. So 2.20 times 0.0350. And that gives us 0.077. Now, before we stop here, you'll notice here we've got 3 sig figs there, 3 sig figs here, and we've only written down 2 sig figs. Sometimes you'll have to write down that extra 0 to make it work. And then that gives us 0.0770 moles of HNO3. And after writing that down, I just realized that I made a mistake up here. This is moles per liter. This should be written as moles. So I'm going to, should be written as molarity, not moles. So I'm going to fix that and put the big M for molarity. Okay, well, I'm glad I saw that before I left this page. All right, next, how many milliliters of 1.50 molar potassium hydroxide are needed to provide 0.125 moles of that substance? Okay, so here we're looking for milliliters, so that's the volume. So let's solve the equation for volume. Volume is, when we solve that equation for volume, we're just going to switch places with the big M and the V. So it'll be number of moles over the molarity. All right, our number of moles is 0.125 moles. And instead of dividing, I'm going to multiply by the reciprocal, and that way the units will be easier to cancel out. So we'll put 1.50 moles per liter. And so 0.125 divided by 1.50, and that gives us 0.0833 liters. Now, it did ask for milliliters, so we just need to multiply that by 1,000, or you can just move it over 3 if you're comfortable doing that, but that gives you 83.3 milliliters of KOH. Oh, Okay, so let's go back to our presentation. There's one more aspect to this that I want to include, and that's what about mass? What if you have mass instead of moles? Because that's often what you're going to have if you're weighing something out. So when you're calculating molarity, sometimes you'll weigh something out, the mass of it. So here it says calculate the molarity of copper 2 sulfate when 39.9 grams of copper sulfate is dissolved in enough water to make 250 milliliters of solution. All right, so what you're looking for is the molarity. All right, so that's what you're looking for, and so molarity is the moles divided by the number of liters. So we just need to convert the grams into moles and then divide by the liters. So here's the grams to get from mass to moles, molar mass. So we use the molar mass to convert from mass to moles. Our molar mass of copper sulfate comes out to 159.62 grams of copper sulfate per mole of copper sulfate. We'll do a little bit of dimensional analysis there. And then we've got moles, and we just need to do moles divided by liters to give us the molarity. So I'm going to do 1 over the liters instead of dividing it multiplied by the reciprocal, and that is dividing anyway. So anyway, that comes out to exactly 1.00 molar copper sulfate. All right. This is commonly used when you're preparing solutions. You weigh out a certain amount, put it in a certain volume, and you want to calculate what your precise concentration is. All right. Now, sometimes we may be interested in a component of the substance. For example, we may be interested in what the concentration of a particular ion is. So here it says calculate the molarity of potassium ion when 57.3 grams potassium sulfate is dissolved in enough water to make 125 milliliters of the solution. So again, we're calculating the concentration. It'll be the number of moles divided by the volume. We've got that volume here, the 125, and we can convert this into the moles. But pay attention here. This is when we use mass to moles and use the molar mass, we're going to get the moles of potassium sulfate. So let's go ahead and set that up. So mass to moles of potassium sulfate, we'll use the molar mass of potassium sulfate, which I calculated earlier to be 174.27 grams per mole. All right, our grams of potassium sulfate cancel out. That gives us moles. And then we're going to do an additional calculation before we divide by the volume, and that is we are going to say, well, how many moles of potassium ion are in every mole of potassium sulfate? Well, it's right there. It's 2. So we'll have 2 moles of potassium ion per 1 mole of potassium sulfate. So our moles of potassium sulfate cancel out. And then finally, we can divide by the volume, and that will give us our concentration. And it comes out, in this case, to 5.26 molar. So let's look at number 66 on our in-class assignment. Okay, so here it says how many grams of solute are present in 50 milliliters of 0.360 molar potassium dichromate. Oh, it was off the page there. Okay, so how many grams of solute are present in 50 milliliters of this? So here, since we're solving for grams, our best stand-in there is going to be the number of moles. Number of moles is going to be the molarity times the volume. So we're going to multiply those. That will give us the number of moles, and then we can convert that number of moles into grams very easily. All right, so that will give us 0.360, and instead of molar, I'm going to write moles of K2 CR2O7 per liter of K2 CR2O7. right? And now we'll multiply that by the number of liters. Here we have it in milliliters, but I'll put it as 0.0500 liters of K2CR2O7. Okay, you'll see the liters cancel out at that point. And now we need to convert the moles into mass. Moles to mass, molar mass. Now, molar mass here, we could use our periodic table. However, I have calculated this a little bit earlier so that we can just put the number in. So I got 294.20. All right, make sure I wrote that down, 294.20. Okay, so clear that. 0.360 times 0.0500 times 294.20. And we've got 3 sig figs here, and so we're going to round that to 5.30. All right, so that gives us our mass of potassium dichromate. All right, next, if 4.28 grams of ammonium sulfate is dissolved in enough water to form 325 milliliters of solution, what is the molarity of the solution? All right, so molarity is the number of moles divided by the volume. And we don't have the number of moles, but we do have the mass, and we can convert from mass to moles using the molar mass. So, N, we'll do 4.28 grams of ammonium sulfate. And we'll need that molar mass, and I happen to have the molar mass here of 132.17 grams of ammonium sulfate per mole of ammonium sulfate. So our grams of ammonium sulfate cancel out. And now we just need to divide by the volume, and we don't necessarily have to put it over here, so I'm going to put it right here. Our volume is 325 milliliters. Of course, we want to put that in liters, so I'll put 0.325 liters. Okay, so clear that. We'll do 4.28 divided by 0.325, and then we'll divide again by 132.17. All right, and you'll see a number that we've got there, 0.0996. So 0.0996 molar, and that is ammonium sulfate. Okay, now we're going to use that number, so I'm not going to clear this yet. I'm just going to leave that in there. We're going to use that number for our next calculation, because the next calculation, what is the molarity of ammonium ion? Well, this 0.0996 molar means 0.0996 moles of ammonium sulfate per liter of solution. We can put ammonium sulfate if we want, but here's what we want to do. We want to say, well, how many ammonium ions are in each ammonium sulfate? And the answer is 2, right? That 2 that's right there. So we have 2 moles of ammonium ion for every 1 mole of ammonium sulfate times 2. All right, and you'll see the number that we get there, 0.199. So 0.199 molar ammonium ion. so NH4 plus. Okay, part D. How many milliliters of 0.240 molar copper sulfate contain 2.25 grams of solute? So here we're looking for the volume. Our volume is going to be equal to the number of moles divided by the molarity. So there's our molarity. We have the mass, and we can convert the mass into moles. So we'll do mass to moles first. So 2.25 grams of CuSO4, so copper sulfate. And we'll need the molar mass of copper sulfate. And our molar mass of copper sulfate, I think that's the one we used a minute ago. Yeah, it is 159.62. 159.62 grams of copper sulfate per mole of copper sulfate. All right, and now we're going to multiply by the reciprocal, which is just like dividing, of course. So 0.240, but instead of molar, I'm going to put moles of copper sulfate per liter of solution. And I'll go ahead and put copper sulfate. All right, so 2.25 divided by 159.62. And then we'll also divide by 0.240. And you'll see the number that we get there is 0.0587. And that is in liters. Since it was asking for milliliters, we'll just take that number and multiply it by 1,000. Or you could just move it over and make it 58.7. But I'm going to go ahead and multiply it by 1,000. And then that way you'll see it is 58.7. So 58.7 milliliters. All right, well, we're going to switch back over and our next topic is going to be the dilution equation. So the dilution equation is a good way for determining the concentration of a solution that you've made by diluting it. And we use the dilution equation all the time. It's just an incredibly useful equation, and it's quite simple. So here is the formula: M1V1 equals M2V2. M, of course, is the concentration, the molarity, and V is the volume. The 1 indicates that it's the stock solution or the original solution that you started with. The V so that's 1. So V1, M1 is molarity of stock solution. V1 is the volume of that stock solution. M2 is the molarity of the dilute solution, and V2 is the volume of the dilute solution. So using this equation, you can calculate as long as you know 3 of these things, you can calculate the 4th thing. So we'll switch over here to number 72. All right, so number 72. And you'll see it says how many milliliters of a stock solution of 7.25 molar nitric acid would you have to use to prepare 0.350 liters of a 0.400 molar nitric acid solution. All right, so here M1V1 equals M2V2. And what we're looking for is milliliters of stock solution. So we're looking for the volume of our stock solution. So we're going to solve this equation for V1. So V1 is equal to M2V2 over M1. And now it's just a matter of putting the numbers in. So M1, our stock solution, is 7.25 molar. And here, I'm not going to put what the chemical is because it's all the same chemical. So 7.25 molar. The volume, let's see, I put the wrong number in there. We want the concentration of the dilute solution here. We're going to put 0.400 molar. All right. And our volume of that solution is 0.350 liters. And then down in the denominator, we want M1, and M1 is our stock solution, and that's the 7.25 molar. So it's real easy to make mistakes. You can see I made a mistake there, but found it quickly enough. All right, so we'll do 0.400 times 0.350. All right, and we'll divide that by 7.25. And that gives us 0.0193 liters of our stock solution. Now, before we finish this, it did say how many milliliters. So to convert that to milliliters, we'll move it over 3. So 19.3 milliliters of our HNO3 stock solution. All right. Now, for this one, it says if you dilute 61.5 milliliters of the above stock solution to a final volume of this, what will the concentration of the diluted solution be? So you can see here it's looking for concentration of dilute. So we're looking for M2. So we'll solve the equation for M2. M2 is equal to M1 V1 over V2. So M1 is for the 7.25 molar. V1 is 61.5 milliliters. And V2 is 0.500 liters. Now, you'll notice that up in the numerator, I used milliliters, and you can use any units that you want in the dilution equation. You can use liters, milliliters, fluid ounces, metric bathtubfuls, whatever. You can use any of those units, and that'll be fine. So I'm going to go ahead and convert this, as long as your units are the same, right? So as long as the V1 and the V2 have the same unit. So I'm going to go ahead and convert this into milliliters and put 500 milliliters. So that's supposed to be a decimal point. So 500 milliliters. You'll see the milliliters cancel out, and that will give us the concentration. So 7.25 times 61.5. And then we'll divide by 500, and that gives us, we'll call that 0.892. So 0.892 molar HNO3 dilute solution. All right, so that's the dilution equation. We will see that show up again and again in this class and in General Chemistry 2. Okay, so the next thing that we want to look at, and this is actually the last thing in for the in-class assignment. So the next thing that we want to look at is solution stoichiometry. You guys remember the roadmap that we talked about in Chapter 3. When we did that roadmap, we had mass to moles, moles to moles, moles to mass. It was nice and simple, and but very, very useful. So very, very useful. So from our mass to moles, moles to moles, moles to mass, what we're going to do is add a few turns, right? Sometimes when you have a roadmap, if you have that roadmap, a paper roadmap for long enough, well, new roads will be added, and your roadmap will be outdated. So what we want to do is we want to add a few things on here, and the things that we are going to add are going to be volume and concentration. So we can, if we're talking about solutions, we can use the volume of A and here volume of B. Use the concentration to get from volume to moles. Again, that's the molarity equals M equals N over V. All right. And using the same equation, we can get between concentration and moles as long as we have the volume. So sometimes you'll see when people do these roadmaps or whatever they call them, they leave this part off and they'll just put it on here. This and this are just opposite equations or opposite operations. One's multiplication and one is division. I'm just going to put them both on there and we'll look at that. So we're going to refer back to this every once in a while because it's useful, and so let's go here. Go back. We're going to do number 79. All right. So on these, so it says what volume of 0.115 molar perchloric acid is needed to neutralize 50 milliliters 0.0875 molar sodium hydroxide. Okay, so since we've been given that, we have that there. What we need to do is we need to come up with a balanced chemical equation. This is a really simple reaction, so I'm just going to go ahead and write it out real quick. So HClO4 reacts with sodium hydroxide. All right, so this is an acid-base reaction, and we get H2O liquid plus sodium perchlorate, so NaClO4AQ. All right, so this is just a straight up neutralization. And you'll notice here that all the coefficients are 1. This is already balanced at this point. So since we've got that, we now want to figure out what it is we're looking for. We're looking for the volume of our acid. And the information that we have is the volume and the concentration of our base. So again, and we also have the concentration of our acid. If we go back and look at this piece of paper, we will see that we've got, all right, you'll see that we've got, let's see, so volume of our, we're looking for the volume of our acid, and here, I'm going to, all right, well, that's not doing anything. Okay. We're looking for the volume of our acid, and we have the concentration of our acid. We have our mole ratio because we have a balanced equation, and we have the concentration and the volume of our base. So we're going to go from the volume of our base to the moles of our base to the moles of our acid to the volume of our acid. All right, so go back over here, and when we go back over here, so we'll do volume of, let's see, what is it? Volume of NaOH to the moles of NaOH to the moles of HClO4 to the volume of HClO4. All right, so our volume of sodium hydroxide is 50 milliliters, and I'm going to go ahead and convert that into liters. So I'm going to put 0.05000 liters of NaOH. And the reason for that is so that we can do the dimensional analysis and cross out the units. All right, so from volume to moles, we will use the concentration, the molarity of sodium hydroxide, which is 0.0875. And that molar means moles per liter. So we'll put 0.0875 moles of NaOH per liter of NaOH. Okay, so now we're going to go from moles to moles. Moles to moles is the ratio, so we'll have 1 mole of HClO4 per 1 mole of NaOH. And then finally, we'll go from moles to the volume using our concentration. We'll need to divide by the concentration of our acid, so 0.115 moles of HClO4 per liter of HClO4. All right, so you'll see liters cancels out, moles cancels out, moles of perchloric acid cancels out, and that's going to give us our answer in liters. Now, you'll have to pay attention if the question asks for if it asks for milliliters or something, then you'll have to adjust for that. But that's easy enough to do. So 0.05 times 0.0875, all right, and then times 1, we don't need to do that, and we'll divide by 0.115. And that gives us so 0.0380 liters of HClO4. All right. Okay, so for this next one, again, we want to start with a balanced equation here. So we've got HCl. It says what volume of 0.128 molar HCl is needed to neutralize 2.87 grams of magnesium hydroxide. So here we've got HCl, and it reacts with MgOH2 solid, and that gives us water, H2O liquid. All right, and then our other thing, so hydrogen plus hydroxide is going to give us the water, and then our other thing is magnesium chloride. Magnesium is +2, chloride's -1, so our formula for magnesium chloride is MgCl2, and that will be in solution. All right, now we need to balance this, and I'm going to start with chlorine because chlorine's the biggest. So we've got 2 chlorines over here. We'll lock those 2 in place and put a 2 here. All right, so now chlorine is balanced. Let's do magnesium next. Magnesium 1 there. We'll put 1 here. And then finally, we'll do oxygen. We've got 1 times 2 times 1. That's 2 oxygens. And to get 2 oxygens, we'll put a 2 there. Now, if you go and look, you'll see that there are 4 hydrogens on each side as well. So that is our balanced equation. So we're looking for the volume of HCl. And so I'm going to take you back over here to our thing. And so we have the mass of our base, and I'm just going to say base is B. We have the mass of our base, and we want to get to the volume of our acid. So we're going to go from mass to moles, moles to moles, and moles to volume. So we'll use that part of our roadmap. All right, so we'll do mass of magnesium hydroxide to the moles of magnesium hydroxide to the moles of HCl to the volume of HCl. All right, our mass of magnesium hydroxide was 2.87. So 2.87 grams of MgOH2. All right. And then we'll need the molar mass of magnesium hydroxide, which I have figured out to be 58.3. So 58.33 actually. So 58.33 grams of MgOH2 per mole of MgOH2. All right, so next we want to go from moles to moles, and that's going to use the equation. There are 2 moles of HCl for every 1 mole of magnesium hydroxide. So 2 moles HCl for every 1 mole of magnesium hydroxide. And then finally, from moles to volume, we'll use the concentration. And here we're going to divide by that concentration. So 0.128, and instead of writing molar, I'm going to put moles of HCl per liter of HCl. And that's going to give us our answer in liters. Now, we may want that in milliliters, depending on what the question asks, but we can deal with that if we need to. All right, so 2.87 divided by 58.33. All right, times 2. Got to remember to, I didn't realize that wasn't on screen there. All right, so times 2. And then we're going to divide that by 0.128 molar. And that gives us 0.769, we will call it. So 0.769 liters of our HCl solution. All right. Our next equation, all right, let's just read it here. If 25.8 milliliters of silver nitrate is needed to precipitate all of the chloride ions in a 785 milligram sample of KCl forming silver chloride, what is the molarity of silver nitrate? So this is not an acid-base reaction. This is a precipitation reaction. So our reaction is between silver nitrate, so AgNO3, and it's reacting with KCl. It's in solution. And according to our solubility rules, it is going to form AgCl. So AgCl solid. And our other thing is going to be what? Potassium nitrate. So KNO3AQ. All right. And I believe this one works out. This one's already balanced. So these are all 1. So that's no big deal. So those are all 1. Okay. So what we want to do now is figure out what it is we're looking for. Well, we're looking for the molarity of silver nitrate. So we're going to arbitrarily call, let's see, the other quantity that we have is the potassium chloride. We're going to call potassium chloride A, and we'll call silver nitrate B. So we're trying to find the concentration of silver nitrate. Let's go back over here. We've got the grams of our sample. So we've got the mass. We want to go from mass to moles, moles to moles, and then moles to volume, or moles to concentration. And to do that, we're going to divide by the volume. Okay. So again, I like to set this up so that I have a roadmap, a plan before I start punching numbers into the calculator. So our mass of KCl our moles of KCl, our moles of AgNO3. Okay, and we're trying to find the concentration. So concentration of AgNO3. So our mass is 785 milligrams. We're going to write that in grams. So 0.785 grams KCl. Okay. So 0.785 grams KCl. We'll need the molar mass of potassium chloride, and our molar mass of potassium chloride is 74.55 grams of KCl per mole of KCl. All right, here moles to moles ratio. The ratio is the ratio of silver nitrate to potassium chloride. That is a 1-to-1 ratio. So 1 mole of silver nitrate per 1 mole of KCl. And then moles to concentration. This one is weird and sometimes will trip people up. We're just going to divide by the volume, and I'm going to go back over here to show you. Right? So when we're going from moles to concentration, we use the volume. So we're just going to divide by the volume, and our volume here was 25.8 milliliters. We'll need to put that in liters, so 0.0258 liters of AgNO3. And sometimes people are like, well, what do I put up top? Just put a 1. Okay, so just put a 1 and you will be fine. All right, so grams cancel out, moles of KCl cancels out, and then we'll have moles over liters, and that's what we're looking for. We're looking for concentration. Okay, so 0.785 divided by 74.55. Right, and then we'll also divide that by 0.0258. And you'll see the number we come up with there is 0.408. And since it's moles per liter, that is molar AgNO3. Okay, so next thing that we want to do here, we've got another acid-base reaction. This is between HCl and KOH. Let's go ahead and read it. If 45.3 milliliters of 0.108 molar HCl solution is needed to neutralize a solution of KOH, how many grams of KOH must be present in the solution? So let's start with our balanced equation. So we've got HCl, AQ, plus the potassium hydroxide, AQ, and H plus OH, of course, makes water, liquid. And then potassium is +1, chloride is -1, so we'll have KCl, AQ. So this one is pretty simple. And when we look at this, we'll see it is already balanced. So all of these are 1. You, of course, don't have to write the 1s, but sometimes it is helpful to look at it that way. All right, so we're trying to solve for the mass of our base. So I'm going to call the base B, and we know the volume and the concentration of our acid. Going back over to this page, we know the volume and concentration of our acid, so we're going to go from volume to moles of acid, from moles of acid to moles of base. That's a 1-to-1 ratio in this case. And then from the moles of the base to, moles of the base to the mass of the base. So again, let's sketch out a plan here. So our volume of HCl to our moles of HCl to the moles of KOH to the mass of KOH. All right, our volume is 45.3, and like what we've done before, we're going to convert that into liters. So 0.0453 liters of HCl. All right, from volume to moles, we'll use the concentration, and the concentration is 0.108, so 0.108 moles of HCl per liter of HCl. So you'll see liters of HCl cancels out. Then we'll do moles to moles, ratio, and the ratio here is 1 to 1. So we'll have 1 mole of KOH per 1 mole of HCl. And then finally, from moles to mass, we use the molar mass, and I calculated the molar mass of KOH a little bit earlier, and I got 56.11 grams of KOH per mole of KOH. So liters cancels out, moles cancels out, moles of KOH cancels out, and that's going to give us our grams of KOH. So 0.0453 times 0.108 times 56.11. There's nothing down in the denominator, so we're good there. And we get 0.2745. We're going to call that 0.275. So 0.275, when we round that, grams of KOH. And that is the answer to that one. All right, well, that is the end of the in-class assignment, but we do have one little thing left. So we're going to go back here, and we're going to wrap up this. I just want to real briefly talk about titrations. So the titration of an acid and a base. Titration of an acid with a base. You can do this titration of a base with an acid. Either one of those will work. But in this case, if you're using the phenolphthalein, then that is going to be titration of an acid with a base. Okay, so usually the way that you get this set up is you take your acid, and you either know exactly how much acid there is, and you're trying to figure out the concentration of the base, or you know the concentration of the base, and you're trying to figure out how much acid you have in this flask. Either one of those will work. It's just which direction on our roadmap are we going when we do the calculation. So here we go. If you put a certain amount in there, and then you do need to put a small amount of an indicator. Usually I put 2 drops of phenolphthalein, and that gives you just the right color. So 2 drops will usually do the job. The burette is a very high accuracy piece of equipment, and you measure by difference. So you get your starting volume and your initial volume, your final volume, and you take the difference. Here you'll see that it is pink, but that's way too pink. That is way too pink. I'll show you what the pink should look like. So when you're doing the titration, before you get to the equivalence point, the phenolphthalein is colorless. When it's in the acidic solution, it is colorless, and it looks like this over here. When you get right at the equivalence point, you get a little bit of that phenolphthalein converted into its pink color. And so this is right at the equivalence point. And then over here, this is what it looks like when you've gone beyond the equivalence point. And so the thing is that at the equivalence point and beyond the equivalence point, the difference there is usually like a drop or 2. And so once you've gone beyond the equivalence point, you're not sure whether you've gone 1 drop or 10 drops beyond the equivalence point. So you have to kind of go slowly when you're doing a titration. Okay, well, that is the end of chapter 4. And it seems like the chapter that should come after chapter 4 would be chapter 5. But in this class, we do chapter 10. So look for chapter 10 for the next and that will be on the next exam. This is the end of the material for the second exam. All right.